Yeah. So good morning, students. Today we will start up with thermal stresses. Okay. So before proceeding to it, just to recollect what we have done in the earlier classes, we have considered about tensile stress and the compressive stress in our earlier classes. So in thermal stress, in tensile stress, the load will be applied axially, okay, away from the body, so which makes the body to expand. Okay, similarly compressive stress is induced when a compressive load, that is when the axial load, when it is acting towards the body, is called as a compressive load. Its effect is to compress the given object or a member, whatever it is. Okay, so now we will see the thermal stresses. Okay, so can anyone tell what do you mean by thermal stress by just by seeing the name? Okay, I don't want any technical. What do you mean by thermal stress? Okay, students,
The stress generated by temperature.
stress generated by,
Due to the change in temperature.
yes, stress is due to difference in temperature. Okay, so what happens when temperature increases in a body? So in mechanical loading, when once we apply the load, it is going to expand or compress depending on whether it is a tensile load or a compressive load. Okay. Similarly, what happens to the same member when it is subjected to a thermal loading? That is, thermal loading means change in temperature. What happens? Can you give some like examples? What you see day to day? Okay. So most of you near to your house or outside your house, you might have seen electric poles, okay, carrying electric wires, okay, thick cables, okay, which supplies power to our houses. Okay, in summer season, you can see that it is very much expanded and it is going to sag like this. Okay, it is going to sag. But in winter season, you can see that the wires are not much sagging, it is almost straight. Have you observed it earlier? Any one of you?
No, sir.
Can
No.
you repeat?
Okay. So just from now, just see what happens. Okay. Or other simple example. Okay. Go and see in your kitchen. Okay. The dosa tawa. Okay. So most of the dosa tawas what we use in our kitchen. Okay. Initially it will be flat. Okay. So after repetitive usage. Okay. See a old tawa. Okay, it will be of irregular shape. It will not be more flat. Just have you observed this? Anyone?
No, sir.
No one. So no one has went to the kitchen.
Can you repeat the question, sir?
If you see in your kitchen the dosa tawa, okay, so it will initially when it is new, it is going to be flat, perfect circle, okay, no unevenness. But after continuous usage, okay, if the tawa is 2 years old or 3 years old, you can see that it is of irregular shape. Okay, it will not be perfectly flat. Have you observed it?
No, sir.
Okay, if time permits, ask your mom to bring the dosa tawa and see what is how it looks like. Okay, after that, not now. Okay, so consider any body. Okay, just a cable. Okay, assume a electric cable. Okay, when you increase the temperature, okay, it is going to expand. Okay, as Okay, the increase in temperature results in expansion of the member. Okay. Let us see. So whenever the material undergoes change in temperature, either increase in temperature or reduction in the temperature, okay, so it either elongates or it contracts. Okay, so depending upon whether it is an increase in temperature or a reduction in the temperature. So in this case, we see a member, a mechanical member, okay, which is subjected to heat. Okay, we are heating it. So we are not going to heat it, just the atmospheric conditions. Okay, the sunlight or all these things, external factors makes them heat, or in the environment. Okay, so in a hot environment, it is going to expand. Okay, so here let us say that the expansion is say delta L due to change in the temperature. Okay, so if this elongation is not restricted, suppose we give some support here. Okay, we give some support here. Okay, we give some support here so that further extension is not possible. Okay, if the elongation is not restricted, then the material does not experience any stress. Okay, but there will be strain. But when we introduce some constraints, when you introduce some support there, then the material cannot expand. Okay, in that instant, additional few stresses will be introduced. So now what we say is there is no restriction. Okay, there is no restriction here. Okay, so as just like that, it is going to expand. Okay, we have a material member subjected to some increase in temperature. So due to increase in temperature, it is going to expand, say, by a small quantity called delta L. If this elongation is not restricted, okay, just if you keep it free, then initially the stress will be there. After that, there will not be any stress, but it undergoes strain. Okay, the stress will not be there, but the strain will be there. Okay, if it is not restricted. Okay, so this stress is called as a thermal stress, and strain due to it is called as a thermal strain. Okay, so the thermal strain is denoted by E is equal to alpha into T. Okay, where alpha is called as the coefficient of thermal expansion. Alpha is called as a coefficient of thermal expansion. Okay, so and how much is the expansion is given by alpha times T into L. Okay, the expansion or deflection, okay, it is given by alpha into T into L. It is nothing but this one. Okay, we know that strain is equal to change in length divided by original length. Okay, so from this we say change in length is equal to alpha T into L. Okay, from that we get it. Alpha is called as coefficient of thermal expansion, and its unit is per degree centigrades. Okay. For different materials, the thermal expansion value differs. Okay, so this slide gives the values for different materials. Okay, so you can go through it later. So now let us see what is the effect. Okay, let us derive the formula for thermal stresses. Okay, so initially we have a member. Okay, we have a member, say of length L. Then it is subjected to some temperature. So it undergoes some expansion. So initially this is L. And after that, due to temperature, then it is going to expand for small t. Okay. In that case, okay, so if we are removing the support, okay, after removal of support only, it is going to expand. If the support is there, it is not going to expand. Okay, so this expansion is given by alpha T into L. The T is a change in the temperature. Okay, so to nullify this deflection, okay, to nullify this deflection, what we can do is we can have an compressive load. Okay, we introduce a compressive load here. Okay, so the compressive load will try to stop this deflection. Okay, so the deflection due to this compressive load is given by PL by AE. Okay, this is a formula what we have done in the earlier classes. Okay, so PL by AE will give the deflection due to compressive load or a tensile load. Here it is a compressive load. So for that purpose, I am introducing this negative sign, which indicates that it is compressed. Okay, so for equilibrium condition, this should be same. The thermal expansion must be equal to this mechanical expansion. So let us equate both the terms. Okay, so when we equate both the terms, we can identify the thermal stress. Can anyone give the formula for thermal stress by equating these two values? So equate the two equations. Okay, equating the above two equations. Can anyone tell what will be the stress? So we have alpha TL is equal to PL by AE. Okay, so L cancels. So P by A is a stress. So stress is equal to alpha into T into Young's modulus. Okay, so the thermal stress is given by minus alpha into temperature change into the Young's modulus. This is the formula for thermal stress. Okay, and negative sign indicates that it is a compressive stress. Okay, and now when the temperature is reduced, then the tensile stress is going to be induced. Okay, so this is the thing. Any doubts in this slide?
No, sir.
So now let us take one example here. So before that, if you want, you can make a note of it. Thermal stress is given by alpha into T into E, and expansion is alpha TL. Okay, so this is the formula we are going to use in this. So in this problem, we have a rod 3 meters long at a temperature of 15 degrees centigrades. Okay, so 3 meters long, 15 degrees centigrades. Okay, this is the initial conditions. Find the expansion of the rod when the temperature is raised to 95. So initially the rod is at 15 degrees. Now it is at 95 degrees. So at 95 degree, what will be the expansion? That is the first part. Okay, can anyone tell the answer for this expansion?
Sir, we will use the same formula, sir, that we have
Yeah,
derived.
expansion, thermal expansion is given by alpha TL. Okay, so alpha TL will be the thermal expansion. So thermal expansion is given by alpha TL. So alpha value is given as 1.2 into 10 power 5. One, two, three, 4, 5. 1.2 into 10 power 5. So 10 power minus 5, that is the alpha value. And difference in temperature is 95
80 degrees, sir.
minus 3. So it is 80 degrees. And length of the rod is 3 meters. So that is 3000 mm. So can, how much? Any values?
So 2.88 mm. Sorry, 2.88 Newton per mm square.
Newton per mm. What is expansion per?
Sorry,
What
sir.
is the deflection unit?
Okay, mm, sir. 2.88.
Okay. So we get the thermal expansion as 2.8 mm. Okay, I hope this calculation is simple and clear. Okay, like this you may get some MCQ questions. Okay, so the second part, okay, so the first part is completed. Now coming to the second part, we have to find the thermal stresses. Okay, calculate the thermal stress when the thermal expansion is prevented, and second condition when it is allowed by 1 mm. So initial condition is we have a rod. Say if both the ends are fixed, okay, if both the ends are fixed, it is not able to expand. Okay, so the expansion is prevented. When the expansion is prevented, what will be the thermal stress? Okay, so that is the first question in the second part. And in the second part, we have this rod and the support is here such a way that this gap is 1 mm. So it is permitted to expand by 1 mm. Okay, can you follow the question? So in the first part, the expansion is prevented. So that is both the ends of the rod is supported. So it cannot expand. But in the second case, we give a small tolerance of 1 mm so that the rod can extend. Okay. So under both the conditions, identify what will be the thermal stress. Okay. So formula for thermal stress, what is the formula for when it is prevented? Okay, thermal stress is alpha T E. Okay, so this is what we have discussed in the thing. Okay, so thermal stress is equal to alpha T into E.
Sir, minus alpha, sir.
Yeah, so leave that is understood. Okay,
But 96 Newton per mm square.
so thermal stress is alpha TE, that is 96 newtons per mm square. So someone has given the answer. That's right. Okay, so that completes this part. The third part is when we allow it to expand by 1 mm. In that case, what happens to the thermal stress? Whether it is increased or it is reduced or remains constant, that we have to see it out. Okay. So now let us see when it is allowed by 1 mm. So what is the expansion prevented? Okay. So when it is not, when there is no support, it is going to expand by 2.8 mm. Okay. When there is support, it is not going to expand. So now we are going to permit 1 mm expansion. So the amount of expansion prevented is going to be 1.8 mm. Can you follow this part? Any doubts here? The amount of expansion prevented. Okay.
No, sir. No doubt, sir.
Okay. So in this case, the strain is going to be change in length by original length. So the thermal strain, what is induced is this 1.8 mm is being prevented. Okay, divided by the original length. Original length is 3000 mm. Okay, so this gives the thermal strain. Okay, so from this you can calculate the thermal stress, which is strain into Young's modulus. So kindly go through it. If you have any queries, please ask me.
Sir, 1.88 is not the original length, no, sir.
What is the formula for strain? Strain
Original,
is change in length by original length.
yes.
The change in length, the expansion, what it is prevented is 1.8 mm. That is the change in length. Divided by the original length is 3 meters. Is it clear?
Okay, sir. Okay.
Yeah, okay. So let us move on to the next problem. Okay. So it is a composite. Okay. So in the similar problem we have done using mechanical loading. Now it is thermal loading. Okay, that's the only difference. So in this case, we have a rod consists of two parts made of aluminum and steel, as shown in this figure. The elastic modulus and thermal expansion for both the materials have been given. Okay. If the temperature of the rod is raised by 50 degrees, find the forces and the stress acting in the rod. Okay, in both the rods, we have to identify what will be the force acting on it and what is the stress acting on it. Okay, all the necessary dimensions and the specifications of the material is given. That is what is the coefficient of thermal expansion and the Young's modulus have been specified. Okay, so can anyone suggest how we can start with this problem? Yes, based on the given data, what we can find out? So what will be the deflection? Yes, tell me, what is the deflection? Total deflection is equal to deflection in steel plus deflection in aluminum. Okay, so what is the formula for deflection? It is alpha T into L. Okay, for steel as well as for aluminum. Alpha for steel and aluminum is known. Temperature rise is going to be 50 degrees. Length for steel and aluminum is known. Can you calculate and tell me what is the total deflection? Anyone working on it? Yes, students.
So 1.35
1 point.
35 mm.
But any others?
Sir, calculating, sir, calculating.
How much time you need here? Only 3 numbers multiplying it. Someone who said 1.357 is wrong.
Sir, 0.06165, sir.
That is also wrong. You can't multiply. You are not going to do manually. Either you are going to use a calculator.
1.10, sir, 1.102.
Almost correct, but not correct. Only 3 numbers you are going to multiply.
Yes, sir. Yes.
This is for steel. Then say similar thing for aluminum. I am using a calculator and I have found out here.
1.1, sir.
Okay, good. Okay, someone has given the right answer. So the deflection is going to be 1.105. Sorry, 1.1025 mm. Okay, so why I given so many decimal places is to give the exact value. Okay, so at least make sure that 2 decimal points are almost same. Okay, okay, try to get accuracy up to 2 decimal points at least. Okay, so now what happens is when the rod is when the temperature of the rod is increased by 50 degrees, okay, what happens is this total deflection of 1.1 mm is expected. But here, there is a space only for an expansion of 0.4. Okay, so there is an expansion of only 0.4 is permitted. Okay, so the restrained deflection, okay, similar to the previous problem, how much deflection is arrested? Okay, the deflection arrested is going to be 1.1 mm is the total deflection, of which 0.4 is permitted. So the restrained deflection is going to be 0.7 mm. Okay, so let us see. The question here is, what are the forces acting on this rod, on this thing? What is the load carried by steel and load carried by aluminum? Okay, so in the initial introduction, I said that thermal stress can be replaced by a mechanical stress or a mechanical load. Okay, so how much load is required? Okay, so in order to compress the rod by 0.7 mm, a compressive force of P is required. Okay, so what will be that P? Okay, that we have to calculate. Okay, the value of P with the compressive load is going to be calculated. So let us find it. Okay, it is going to be applied axially. So in this case, the deflection is 0.7. So what is the deflection under mechanical loading? What is the formula for deflection? Formula for deflection under mechanical loading. Say under a compressive load, what is the formula?
P into L divided by A into E.
Yes, we know that delta is equal to PL by AE. Okay, for aluminum and steel, because aluminum is also going to compress, steel is also going to compress by this compressive load. Okay, so using this relation, we know what is the length, we know what is the area, we know the Young's modulus. Okay, so the unknown value is P. So calculate what is the load. Do it first. So I am also calculating along with you. Yes, done. Any answers? We know the values of length, area, Young's modulus. Calculate P. Here P is going to be same. It is the same compressive load. Load is going to be share. Load is going to be same. Okay, already we have done some problems based on that. Yes, done. Students, whether there I am in the class. Yeah, I think I'm there. So kindly respond, ba. Is anyone is working?
Sir, 0.55, sir.
Don't tell number with units. Hey, how much time you need, pa? A simple calculation. Is any value? So kindly hold on for some. Yes, students, have you worked out?
Sir, 42.078
Yes.
kilonewton.
Yeah, that's great, but too much time. Okay, so 42 kilonewton will be the answer. Okay, so that is the answer for the first question. So the second question is, what is the stress? Stress is force by area. Okay, so stress is equal to 42 in steel, 42 kilonewton divided by area of steel. Similarly, for aluminium, 42 kilonewton divided by area of aluminium. Answers? So you are all struggling a lot in calculation, or just simply sitting? I'm not sure. Okay. Whatever is your difficulty, kindly update us so that whatever the possible extent I can support, I can do it. Do you have any trouble in calculating? Yes, for steel and aluminum, what is the stresses induced?
Sir, for steel it is 60.86 and for aluminum it is 21.77.
Always tell with units. Okay. Okay. So for steel 60 megapascal and for aluminum it is 21 megapascal. Okay. So kindly improve your speed in calculating. Okay. With this speed, it will be very difficult for you. Okay. Okay. So we will move on to the next question. Okay. So there is a rigid horizontal bar of negligible mass connected to two rods as shown in figure. Okay, so there's a rigid horizontal bar, and this horizontal bar is supported by two further rods like this. If the system is initially stress free, okay, there is no initial stress, okay, find the temperature that will cause a tensile stress of 90 megapascal in the brass rod. So this is the brass rod. In this brass rod, the stress is going to be 90 megapascal. Okay. Assume that both the rods are subjected to change in temperature. So both the rods are subjected to same temperature change. Okay. So we have to calculate what will be the temperature change which can induce a stress of 90 megapascal in the brass bar. Okay. So, so how to do it out? Okay. So we know in the question it is given that the stress in brass bar is 90 megapascal. Okay, so from this, can you calculate the area? Because sorry, can you calculate what is the load acting in brass? The area is given. Area is 1200 mm². So stress is 90 megapascal. From this, can anyone tell me what will be the load acting in the brass? Any answers?
So, but the system is stress free, sir.
What the?
The system is stress free.
Yes, initially it is stress free. After that only there will be a temperature difference. Okay, after that there is some temperature difference which makes the stress in the brass is 90 megapascal. Okay, so the stress in brass is given as 90 megapascal, and we know the area of brass, which is 1200 mm square, which is given in the question. So find the load. Force is nothing but stress into area. Stress is 90 megapascal multiplied by area is 1200 mm square. Calculate what is the load. Any answers? How to convert megapascal to newtons per mm square? Yes. What is 1 megapascal?
Sir, it is equal to 90 Newton per mm square only, sir.
Yes. So megapascal and newton per mm square are same. Okay. So now find this load.
So 108 kilonewton.
Yes, 108 kilonewton. Okay, that completes the first part. Okay, then after that, if load in brass is 108 kilonewton, what will be the load in copper? Okay, so for that, we have not given any stress value in copper. Okay, so instead of that, what they have given us, it is going to be a straight horizontal bar of negligible mass, and it is being fixed here. Okay, so let us take this point as some O or something. Let this be the origin. Okay, let this be the origin, or let this be some point A. So equilibrium condition is sum of moment about point A should be 0. Okay, so what is moment about A? There are two forces. So here force is going to act upwards, and here the force is going to act downwards. Okay, so equating it, so this is force in B, this is force in copper, this is force in brass. Okay, so 5 times force in brass must be equal to 3 times load in copper. So for brass, we found that it is 108. So 5 into 108 is 540. 540 by 3 is 18. Okay, so PC is equal to 118 kilonewton. Is it right? Can you follow it? Any doubts here? Students, can you follow it?
So 540 divided by 3 is 180, sir.
Purpa?
So 540 divided by 3 is 180, sir.
Yeah, 180. I have written 118. Okay, 180. Okay, so once the load is known, you can find what is the stress. Stress is force by area, that is 180 kilonewton, by area is 1500 mm square. Okay, so you can calculate it. Okay. So then let us find the deflection. So what will be the deflection in each brass and copper? Okay, so before that, let me erase the unwanted portions here. Okay, okay. So here, this is the thing. So this is the loading condition. So the net effect is going to be like this. If it is going to expand like this. Okay, and here we see a expansion of thermal expansion of brass is 18, and for copper it is 16. So thermal expansion of brass is greater than copper, which means that brass is always going to expand more. Okay, when the material is having a higher expansion, okay, higher thermal expansion, then it is going to expand more. So in this case, brass is going to be expanding more compared to copper. Okay. So before that, we have found delta, which is PL by AE. Deflection is nothing but PL by AE. So for brass, we know the stress value, we know the length, we know the Young's modulus. Similarly for copper, so we found the deflections. Okay. So now, so the expansion of brass is going to be more. So from this similar triangle, so here you can see that this part, this portion, okay, this is going to be the deflection here. So this deflection is given by thermal, the copper is going to expand, okay, due to thermal expansion, that is due to temperature difference, minus due to the actual load. Okay, the actual expansion is delta is C, delta of copper. Similarly for the brass, okay, we have deflection due to mechanical loading minus deflection due to thermal loading. Okay, so that is what it is mentioned here. So from these are similar triangles. So using the law of similar triangles, the thermal expansion minus mechanical expansion is this vertical distance divided by the horizontal distance is 3 meters here. That should be equal to a mechanical expansion of brass minus thermal expansion of brass divided by the total horizontal distance is 5 meters. So from this similar triangles we get it, and this must be equal to the thermal expansion, which is alpha TL. Okay, this must be equal to alpha TL. So from this, okay, you calculate what will be the delta T value. Okay, work it out. Can you please work it out? Yes. Can you calculate or not, pa? So for thermal expansion for copper, what is the it is formula for thermal expansion is alpha TL. Okay, the alpha value for copper it is 16 micrometer, so 10 power minus 6. Okay, that should be included. Okay, 16. Then change in temperature is not known. Length of copper is 3 meters. Okay, that will be this delta C. Then minus for delta C, here we have got it is 3 mm. So this will be 3 mm divided by 3. That should be equal to delta of brass. Delta of brass is 1.8 mm minus thermal expansion of brass is given by alpha TL. The alpha for brass is 18. Temperature is not known. Length is 2 meters. So equate it and get the value of delta T. So these values are known. Substitute here. Okay. Okay, so substitute the value for thermal expansion of copper is 0.05 T. For normal expansion of copper is 3 mm. So equate this and get the value of the temperature. The temperature will be around 56 degrees centigrades. Okay, so just check it out. The answer is around 56 degrees centigrades. Kindly work it out. Can you follow this problem? Any doubts in this? Students?
Sir, can you explain the triangle part once?
Yes, so here, so in this case, we know that as the thermal expansion of brass is higher, okay, brass is 18, for copper is 16. So brass is going to expand more compared to copper. Okay. So in this triangle, okay, so here the load is there. For copper, the load is 180 kilonewton is acting like this. And here for brass, it is 108 kilonewton is acting like this. Okay, upwards, and this is acting downwards. So the net effect, okay, so the deflection at this region is given. So the deflection here, okay, is given by thermal expansion of copper minus normal expansion of copper, that is due to mechanical load, and this is due to thermal load. This is thermal load minus mechanical load. But for the extreme end, okay, for the extreme end, brass expansion, mechanical expansion minus thermal expansion. Okay, so this value. So these two are similar triangles. For similar triangles, what we can do is we can have the ratio between vertical height and the horizontal distance. So here the vertical height is delta, that is thermal expansion minus mechanical expansion, and the horizontal distance for the first triangle is 3 meters. So for that only it is 3. That should be equal to the vertical distance for the second triangle is mechanical expansion of brass minus thermal expansion of brass divided by, this is the overall horizontal distance for the second triangle. The horizontal distance is 5 meters. So divided by 5. So this completes the first part. This is our first part. Okay, equating the similar triangles. In this, what is this thermal expansion? Thermal expansion is given by alpha TL. There is a formula what we know and what we have used in the previous problems. Okay. So in this you substitute delta T, the thermal expansion for brass and copper you calculate separately and substitute here, and that will be in terms of temperature because we don't know what is the temperature. And delta mechanical expansion for brass and steel we have calculated here. So you can substitute that and you can calculate the value of change in temperature, which will come around 56 degrees centigrade. Can you follow it?
Yes, sir. Thank you, sir.
Yeah. Similarly, this problem, you try to work it out. Okay, already it is available in the lecture slides. You can go through it. Okay, and do it on your own. Okay. Okay. So the next important part is about principal planes and principal stresses. Okay. So we are always whenever we go for designing or anything, okay, so we want to know what will be the maximum stress induced in that. Okay, so accordingly only we can select a suitable material, because for every material there is some stress values. Okay, so the stress which is induced should not be more than the capacity of that material. Okay, for that it is very important to identify what will be the normal stress which is acting on the given member. Okay, so for that purpose what generally we do is, we will there are infinite number of planes which can pass through any point. Okay, so if there is a member here, so assume that this is a member and there is a point in it. So through this point we can draw n number of planes, say a plane like this, a plane like this. Sorry, I'm not drawing it properly, passing through it. Okay, so we can draw so many planes like this. Okay, we will have infinite number of planes which is passing through a point. Okay, and on each plane there will be different stresses. Each plane there will be different stresses. Say for example, when you consider a normal tensile load. Okay, so we have a member which is subjected to a tensile load. Okay, no other thing we are considering. Okay, in that case, so if this is the cross sectional, okay, if you want to see what is the stress acting in the vertical section. Okay, in the vertical section, okay, stress is force divided by area. Okay, area is this cross sectional area. Suppose, okay, suppose if we consider a plane like this. Okay, if we consider a plane like this, we have to see the equivalent force here. Then here this will be your cross sectional area. Okay, so in every plane the area differs. So as per that the normal stress is going to differ. Okay, so for that only we use this principal stresses. So there will be one plane in which the normal stress will be maximum, and that plane is called as the principal plane. Okay, otherwise maximum principal plane. Okay, so for this tensile loading, only this vertical plane will have the maximum stress. Okay, so that vertical plane will be called as a principal plane if there is only one load which is acting like this. Okay, so similarly there will be this plane will have a maximum stress since the load it has the normal stress is maximum. So that stress is also known as principal stress. Okay, 1 minute, Raja. 12 மணிக்கு வராங்களாங்க, கொஞ்சம் வந்து சூசைட் இருக்க மாட்டோம் நீங்க. Okay. Yes. So similarly, as I said, one plane will have maximum value, another plane will have minimum value. That minimum one is called as the minimum principal stress. Okay, we have maximum principal stress and we have minimum principal stress. Okay, so consider and in the principal planes, the shear stress is going to be 0. Okay, so that is more important. Okay, this is an important question, MCQ. Okay, what happens in the principal plane? What is the shear stress value in the principal planes? Okay, the shear stress in the principal plane is always 0. Okay, in the principal planes, in the max, well, shear stress is going to be 0. Let us see how it is. Okay, so consider a one-dimensional stress system. Okay, so assume that a load is acting tensile like this. Okay, so this is a tensile load, and EF is a vertical cross section. Okay, EF is a vertical cross section, and we consider another plane called GF. Okay, or FG. We have another section called FG, which is at an angle of theta with the vertical plane. Okay, it is at an angle of theta with the vertical plane. So the cross-sectional area, okay, the cross-sectional area along FG, okay, of this plane, this cross-sectional area is given by the vertical cross-sectional area divided by cos theta. Is it right? Any doubts here? Can you follow it? Okay. So now let us see what is the normal force. The normal force acting along FG, along this plane, it is going to be P cos theta. Okay. So along this plane, the force acting will be P cos theta. Similarly, the stress is going to be force by area. Force is P cos theta. Area is A by cos theta. So the normal stress is going to be P by A. P by A is nothing but your sigma value, and cos into cos will be cos square. So the normal stress along this plane is given by sigma cos square theta. Similarly, the tangential stress, otherwise called as the shear stress, is perpendicular to it. Okay, shear stress is perpendicular to it. So in that plane, so here the force is P cos theta. So in the perpendicular direction, the load will be P sin theta. Okay, so normal force and tangential force. Okay, normal force and a tangential force. The tangential force is P sin theta divided by area, which comes to sigma by 2 sin 2 theta, because when you simplify this, it becomes sin theta cos theta. Sin theta into cos theta is nothing but sin 2 theta divided by 2. Okay, so that is written here for simplification. So from this equation, we find that the normal stress is sigma into cos square theta, and tangential stress is sigma by 2 into sin theta. So to get the maximum normal stress, okay, the normal stress purely depends upon the cos value. Okay, when cos value is maximum, the normal stress is going to be maximum. Okay, so when cos is maximum, when cos will be maximum, okay, what is the value of what is the maximum value of cos theta? Anyone? What is the maximum value of cos theta? Students? 1. Okay. So when cos will be 1? When theta is 0 degrees. Okay. So when theta is 0 degrees, that is when at the plane perpendicular to the applied load, that is on this plane only. Okay, on this plane, you will have the maximum normal stress. Okay, that is what initially also I informed you. Okay. Then shear stress. Coming to the shear stress. Okay, so this is the formula. Okay, so this is the formula for shear stress. and it can take a maximum value, okay, whenever sine 2 theta is maximum. We know that maximum value of sine theta is going to be 1, okay, and that 1 is going to occur when theta is 90 degrees, okay. So we get 2 theta is equal to 90 degrees, or theta is equal to 45 degrees, okay. So 2 theta is equal to 90 or 270. So from this, theta will be 45 or 135. So when at these inclinations, okay, when the plane is inclined at 45 degrees or 135 degrees, 45 degrees means like this. So you will get maximum shear stress. So you can see in this figure, okay, this is inclined at 45 degrees to the vertical plane, and this is inclined at 135 degrees to the plane, okay. So in these two planes, we will have our maximum shear stress, okay. So whenever a member is subjected to pure tension, both tensile and shear stress will be induced in it, okay. So that is what we have founded. So the maximum normal stress will be perpendicular, it will be available in the perpendicular cross section, and maximum shear stress will be available at an inclination of 45 degrees or at 135 degrees. 45 degree and 112 is nothing but just opposite to each other, okay. No much difference, okay. So any doubts in this part?
No, sir, no doubt.
No, sir, no doubt, sir.
Yeah, thank you. Okay. And these are the important MCQ question. Okay, when the member is subjected to pure torsion, okay, when the member is subjected to pure torsion or pure tension, then tensile and shearing stress will be induced. And when it is subjected to pure compression, compressive and shearing stress will be induced. Okay, this may be MCQ questions for you. So this slide is very important. Okay. Okay, so we have another 10-15 minutes. So we'll do one problem. Okay. So in this case, we have a rectangular bar of 1000 mm square subjected to 20 kilonewton. Find the normal stresses at an angle of 30 degrees. Okay. So this is a question given to you. So we have a rectangular bar of 100 mm square subjected to a tensile load of 20 kilonewton. Okay. And we have to find what is the normal stress and shear stress on a section which is inclined at 30 degrees to the normal cross section. So this is the normal cross section. So this is the normal cross section. To this normal cross section at an angle of 30 degrees, we have another section. We have to find what is the normal stress and shear stress along this section. Okay, so that is a question given for us. So it's a direct formula substitution only. So first, the stress is nothing but force by area. Force is 20 kilonewton by 1000. So which is 20 Newton per mm square. And normal stress is sigma into cos square theta. We know the formula. This we have derived it in the earlier slide. Normal stress is sigma cos square theta. Tangential stress is sigma by 2 sin 2 theta. Okay. Just use these two formulas and calculate what are the normal stresses. And theta value is going to be 30 degrees. Okay. All these things can be MCQ questions for you. Okay. Anyone, we'll give all the data and we'll ask what is the normal stress, what is the shear stress, or at what plane you will have maximum stresses this much, something like that. Okay. So more number of MCQ questions are possible in this topic. Okay. Similarly, when you see this problem, so we will have two wooden pieces connected together. Okay. So we have two wooden pieces which are connected together like this along AB. What is the force required? Okay. What is the maximum force P that can be applied if the allowable shear stress is 1.2? Okay. So here also this is 30 degrees. So we have this will be your normal plane. If this is 30 degree, what will be this angle? If this is 30 degree, what is this angle? because this is the inclination with the normal plane.
30.
Okay. This angle, what I have marked.
60.
If this is 30, this angle will be 30. Okay. But
Yes,
we
sir.
need this angle 60 degree. Okay. So and along with the normal cross section, the angle of the given plane is 60 degrees. So shear stress is given by they are given the allowable stress is 1.2 allowable shear stress, and the formula for shear stress is this. Okay, the formula for shear stress is this. So from this we can get what is the value of sigma, and then you can the area is known. Area is 10 into 10. From this you can calculate what is the load P. Can anyone find the value of P? Any quick solution? What is the value of P? So from this equation, find what is sigma. That sigma is nothing but force by area.
Two 2.77 into 10 to the power 4
Unit.
Newton.
Okay, don't say 10 power 4 Newton. Okay, you should
Kilo.
give. Okay, but okay, the stress is 2.1 and 27 kilonewton. Is it right?
Okay. Okay, sir.
Don't
Okay.
say it is 2.7 into 10 power 4 Newton. Okay, that is not technically right. Okay, but mathematically it is right, but technically you should give in kilonewton or something.
Okay, sir.
Okay, so I think okay, so only these properties we will see and then we will wind off. Okay, so the important properties of principal stresses are the principal directions are mutually perpendicular. Okay, and it will along the normal stresses will have maximum and minimum value along the principal axis, and shear stress is going to be 0 in the principal plane. Okay, so this is the important property of principal planes or principal stresses, and we will do two-dimensional stress system. Okay, in case of two-dimensional stress system, there is stress acting in both x and y direction. Okay, the stress is acting in both x and y direction. Then no need to derive the formula, directly remember this formula. Okay, normal stress is given by sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta. Similarly, tangential stress is this, resultant stress is this. Okay, and the angle with which the resultant makes with the normal to the given plane is called as the obliquity angle. That obliquity angle is given by tan inverse of tau by sigma n. Okay, so with this formula, okay, all these are direct formulas only. So with this formula, you can try out this problem. Okay, so all the data are given, direct formula substitution, you can get the values. Okay, so I want you to work out these already one problem I have given and these two problems. So next class we will go with geometrical method. Okay, so these are theoretical way of finding it. Let us see how we can do it geometrically. For that, for tomorrow's class, kindly have your drawing instruments with you. Okay, I want to see everyone drawing, and I want to see your notebooks tomorrow. So with this, I conclude today's lecture. Okay. and